Hello everybody. Today I'm going to talk about how temperature affects rates of reactions. We'll take a model that's called the Arrhenius Equation. I'm just going to focus on its form in regards to how first order reactions are affected by temperature. Most reactions, the rate increases with increasing temperature. That is not exclusive. You'll find, particularly those of you going on into biological sciences, biochemistry, subjects like that, you'll see that there are distinct classes of reactions where actually the rate decreases when you increase temperature. For example, with certain enzymatic reactions. You can even have changes of regimes where sometimes it's increasing and then there's a change basically in what's going on behind the scenes as you increase temperature, and the rate can decrease, the reaction can stop altogether. So this is one of the common cases, but I don't want to make it like it's exclusive. The model we're going to study, and it is a model, is called the Arrhenius Equation. It's a description of how the rate constant, so this is the rate constant, and we'll make it for a first order process just to keep it simple. So this will have units of inverse time. Is related to this, well, I'll just explain the components of this equation. Here at A, we've been using A a lot for concentrations, for identities of particular chemical species. Here, A does not mean that. A is what's called the pre-exponential factor. Or it's also called, both names are used commonly, or the frequency factor. It will carry the units of the process we're studying. For studying first order, this will have units of 1 over time, such as inverse seconds. We have the exponential function e. Inside that lowercase e, the exponential function, there's another e. That's activation energy. And that's basically, if you think about it, you have a reaction going, let's say, A to B. And so you start off over here. Let's just make this potential energy of some form. You start off with A, and let's say B is lower energy. For the sake of argument, it doesn't have to be. There's a hump in energy as the molecule or molecules react that represents a barrier that you have to get over. We'll talk about more of the details of that in a second, but if you draw a line across like that, this height here is the activation energy. We're only going to focus on the forward reaction going from A to B. So that would be the activation energy for the forward reaction formally. So we call this activation energy. And it's typically, if we have it in the form with the gas constant R, it'll have energy reported in kilojoules per mole commonly, or joules per mole. It's energy per mole. How we scale it will depend on how we treat R. If we have R in joules per mole Kelvin, then we have to, a lot of times it's tabulating kilojoules just for convenience. We would have to convert it to joules per mole. Whatever goes inside the exponential has to be dimensionless. R is the gas constant. And if we're working in the scaling of joules and moles, I would use the form of 8.314. You can look up more sig figs if you want. Joules, mole, times Kelvin. And T is temperature. I don't want to write too low on the board. And that will be in units of Kelvin. Another K, but we have a certain number of symbols we use over and over, and K's tend to be a big one in this course. So this is called the Arrhenius Equation, and this will be the way I have it set up for a first order process. All of this is on the notes at approximately page 13 of the unworked out note set, so you can read over it in some detail. Let's just think about this mathematically a little bit without just looking at what's going on here. So in this equation, if you have just in the form it's in, it's going to have an exponential form. When so if I plot something like 1 over t versus k, usually we're not going to plot it like that, but you could. The way this would look would be, this is an exponential function here on this end where you have 0. This is where t is going to infinity, and then out here, because this is 1 over t, when you get way out here, keep going, you know, t is going to 0. The way this is going to look is like that, right? The point here when t goes to infinite temperature, now you're not going to have a reaction that's at infinite temperature, but this would be the limit. Here, this would blow up, the exponentials, what's inside it would go to 0 because the temperature is getting huge in the denominator, right? So just put in a calculator, put in a function like e minus 1x, and put x in as 1,000 or 10,000 and see what happens. So it's going to, on your calculator, it's going to go to 1 because that's going to be e to the 0, which e to the 0 is equal to 1. If it's e to minus 0, it's still 1. In this case, we have this pre-exponential factor, so that would be a over here. And then when you go way out there, it never actually goes to 0. Your calculator will read it to 0 if you keep putting in tiny, tiny numbers. But it's really just, it's limiting towards 0. So it has this type of curved shape like exponential decay. What that's basically telling us is that at very high temperature, the rate constant is going as the pre-exponential frequency factor. The reason why is what makes up the frequency factor. I'm just going to write it with a squiggle as it's proportional to, if you can think of it, related to two things really. It's related to frequency of collisions. Now I'm going to just describe this from a gas phase process to make it simple, but this would be collision frequency. So you can think of a frequency having units of inverse time, and there's other ways of scaling it for other higher order processes. But let's just take first order case. And that's, so there's a direct relationship between how things collide, how frequently they collide, and the frequency factor, or the pre-exponential factor. Just to put it in perspective, in the air, N2 and O2 molecules at 1 atmosphere pressure, they're colliding about 10 to the 9 times per second. There's a lot of collisions in the gas phase at room temperature. That's like 1 billion collisions per second. So it's not trivial. And then there's also another factor, there's different symbols used. I believe I used P in the notes. This is a steric factor. It typically is between 0 and 1. It's a scaling factor that relates to the shape of the molecule or the atoms. You would think atoms would be perfectly 1. They're not. They sometimes are close to it because there's more to it than just the physical shape. It deals with quantum mechanical effects and so forth that we will not go into. But just take note, if the big picture is that very high temperatures, the rate constant becomes very similar to a collision frequency represented by a collision frequency. And so in gas phases, that can be big numbers on the orders of millions or billions, and so at room temperature. So, but we don't typically observe rate constants with that type of a huge number. The reason why is because we have this multiplicative exponential on it, and we have to take into account the activation energy. So the activation energy shown over here, I'm going to draw a bigger picture here in the middle of the board, and this is similar to the picture you'll see on page 13. If I have energy, and the energy could be typically, we usually use the potential energy just to give things a scaling. And you have here, if you have reactants, then you have this energetic hump, and you go into products. Now this, when I'm looking at this right here, a few things I want to take note of. I'm going to just draw a line across here. I'm only focusing on the forward reaction of reactants to products. I'm not going to worry about a reverse reaction. The activation energy is this hump right here, the distance from this baseline to the apex of the curve. Hopefully I drew it fairly okay. Also take note is this is not a thermodynamic energy. It's related to kinetics. The distance between the reactants position that defined a baseline and a good baseline for the products, this spacing here could give you, for example, if you scale this axis correctly, the enthalpy of the reaction. This reaction, clearly the products are lower energy than the reactants. We can imagine energy was lost as heat. This would be for an exothermic process where you see the products at lower energy than reactants. If they were higher, like you could have them up here, you could still have a hump, but it would look more like, let me just, I have to erase something here. Let's make this potential energy. Here's the reactants. There's a hump. And here's the products. This distance here for the forward reaction is still the activation energy. This is endothermic. This is endothermic here because the products are higher energy than so the distance here, that would give you delta H. This is endothermic. The products are higher energy. You can imagine the system, the chemical reaction, taking in heat from the surroundings. So that would look different, and I often have that on exams. People tend to mix those two things up when they look at diagrams. I'm not sure why. So this is a basic idea of what's going on. There's at the top of this, there's what's called there's a transition state that's occurring here, and we call the chemical species that lives here the activated complex. There's really not much in this course that we can do with this. It's just terminology basically for us. So I'm not going to put a lot of emphasis on this concept here. This is transition state theory, which goes on into its own subject. I'm going to focus on more pragmatic things that are needed to go on in chemistry and to be successful in things like the MCAT. I do teach courses where I actually spend weeks on that topic, so I'm not leaving that discussion off because it's unimportant. It's just that in general chemistry we have more important things than theoretical aspects of transition state theory to talk about. So one of the types of equations, and I'll do the calculation in the, well, first let me could say this, is that we have this equation here, and remember how I drew before this curved relationship. If I drew K, and maybe I want to do 1 over T, we get something like this. So a linear way, there's nothing wrong with that, but we can log this thing out and write it as ln of K, and I'm choosing to use the natural log, is equal to, you're going to have an ln of A term here. Remember, let's say ln of, I'll just use a and little b, ln of A times, the natural log of A times B is ln of A plus ln of B. So I'm using that property, and then the natural log is and the exponential inverse function. So that just comes out the what's inside the exponential. So you're going to have negative EA over R, and I'm going to write it like this: 1 over T. So this is a linearized form of the Arrhenius equation in the form of y. And here's your intercept B. And then when you look at this, if you plot this as x, this could be x, and then this would be the slope m. So right here is the slope of the curve, and that equation is on the bottom of page 14 going into page 15 of the note sets. I have an Arrhenius plot represented here. So what you'll plot is ln of k versus not t, but 1 over t. So it's very similar to what I did before, except now what we're doing is logging out one of the axes. So it's a semi-log type of plot, and the way this would look, we'll extrapolate some points back. It goes like that. It's going downward. The intercept here is ln of a. So if you make a plot experimentally, you have a number here. You take the exponential of that number to get a. You can get the frequency factor from it. A lot of times I ask on tests, what can you get from something? And somebody will say, well, I can't get a, I can get the ln of a. That doesn't mean that. It means you can do a simple mathematical operation and get a out of this. It's going downward slope because the slope is negative EA over R. So the slope equals negative EA over R. So if you're on Excel and you make a plot, you can simply take that number, cross multiply by the gas constant R, and the activation energy for our purposes will be a positive value, a positive activation energy. So you cross multiply or multiply through by -1, I should say, and the activation energy will be a positive value. If you are interested in making a plot on your own, I have some data that you on page 15 going into 16 that you can make your own. So if you want to try to do this, see what it looks like, you probably will do things similar to this in lab as well. So that's an activation energy. This is Arrhenius plot in a linear form, and so you can work on a skill builder if you care to. What we'll do in the next lecture is briefly, I will work, well, there'll be a shorter video. You can take these, the Arrhenius equation, and take 2 points, take like temperature T1 and T2 with 2 rate constants K1 and K2, and combine them together and get a form. I'm going to let you derive that. It's very simple to do. Just add or subtract 2 equations together, and you can get this form, provided the activation, it has the same activation energy. There's no change in regime. It's the same equations applicable. You can get a form like this. This would be on page 16 of your notes. We'll solve a problem with this time. Usually the way this goes, you'll say, like, I know what's going on with temperature and the rate constant from an experiment or from a book at a certain set of points. And then they might say, well, what at T2, another temperature, this could be 100 Kelvin, and you have rate constant, this could be 200 Kelvin. And your question is what's the rate or rate constant at that new temperature? Very common question. We'll work a problem like that next time because we're running a little low on time here. So this has been a discussion of the Arrhenius equation, and one of the basic models that describes how temperature affects the rates of reactions. So on that note, I'll talk to you later. Take care.